Hello, everyone. Welcome. We're very happy to have Evita Nestoridi here today, who will tell us about card shuffling. And how would you like people to ask questions?
Oh, they can unmute, they can use the chat. Either way, feel free to interrupt me if you see anything on the chat and I don't. Whatever makes people feel comfortable.
Okay, sounds
But
good.
I do want people to interrupt. That I want to say, okay, please. I don't want to be talking to myself. Thank you so much, Simon, for the invitation, and hi to everyone. I wanted to talk to you about some basic things about card shuffling and the math hidden behind it. I don't know if you've ever heard about card shuffling before and how it is mathematically formulated. So we always start with a deck of n cards and distinct cards for us. Okay, so you buy a deck of cards from the store, it comes with 52 different cards. So the most common way to shuffle, and we will get to this later, but I want to start with this at least. So the most common way is what is called riffle shuffling. Okay. The riffle shuffle. So I will define this mathematically more rigorously, but for now, you cut the deck. So the first step is, you cut the deck in roughly half. So into two equally sized piles, equally with, quotation marks, because, when we do it in practice, we never stop to count. It's roughly equal. And then we riffle. Again, I will make this more mathematical later on. So, you have your piles and we just grab them and do this trick that you have probably seen many people do. That's called riffling. So, cards fall from the two piles in some order, and then at the end you have the deck back together. So the question, of course, that we will be discussing is how many times, let's write it this way. How many times do we need to repeat this to get the deck shuffled well? And all of this, I'll try to make rigorous to a certain extent, at least. So this is, probably the most famous theorem in card shuffling. It's about the riffle shuffles. So Bayer and Diaconis proved that if you have n cards, it takes 3/2 log base 2n to shuffle the deck. So if you take as many steps, so 3/2 log base 2, 52, plus a little bit more, then you're totally shuffled. If you do a little bit less, then you're totally not shuffled. That's what they proved, basically. And before continuing to the first model that I'll analyze, because this will be the second model we'll analyze today, I want to make a note. People who play with magic might know this. If you do perfect riffles, meaning that, you cut your deck perfectly in half and you can do one card from the right pile, then one card from the left pile, one card from the right pile, one from the left, and so on. So you alternate. If you do this 8 times, then you're back to where you started. So performing 8 perfect riffle shuffles will bring you back to the initial configuration. So people like Percy Diaconis, who can do perfect shuffles, can easily cheat, because surely one would think that after 8 shuffles, you're very well mixed, but in reality, he knows how to trick you and cheat, because he knows that he's at the initial configuration. Okay, but let's start with an easier shuffle at first to analyze, and then we'll get to the riffle shuffles. These two shuffles are very connected, actually, even though at first it doesn't seem so. So I'll start with what is called random to top. And please ask me any questions, especially the definitions of the models, which I'll start doing now more carefully. If we don't understand what the process is, then it doesn't make any sense to continue. So again, we have a deck of n cards. Now the shuffling rule says to pick a card uniformly at random. Pick, I'll explain what that is in a moment. Okay, so we pick a card uniformly at random and we move it to the top. So this means you have your deck, and then each card is equally likely to be selected. Okay, that's what it means. It's not like you prefer the ones on top to the ones on the bottom, equal weights. You pick one, you move it to the top. Then you do this again and again and again, and that's a way to shuffle the deck. Obviously, it's not the way that we suggest that people shuffle a deck of cards. We will see it takes quite some time, but this model comes from computer science. It's called the setting library, and it's very connected to how computers behave.
We go ahead and give you about.
Oh, okay. I thought there was a question, but no. So the way that our computers work, the documents are on a pile. And, if you want to, for example, find a picture, your computer goes on this pile and searches for your picture after checking, one after the other, all the documents. When it finds the picture, it brings it to the top because it's very likely that you might need that picture again very soon. So this is where this comes from. Now, this is a theorem due to Aldous and Diaconis, and we will be discussing this, that says that it takes n log n steps to shuffle well, according to this shuffle. Okay. Are there any questions about the model? There is a generalization, which there's no point in doing today, where, you don't pick cards uniformly at random. It might be that you favor some cards compared to the others, but then the math ideas are quite similar. The answer would be different. It won't take necessarily n log n steps. It will depend on the weights that you put. But if every card is selected with probability 1 over n, then n log n is the mixing time, the shuffling time. Okay, so let's start talking a little bit of math. So how to study card shuffling? There are many ways, there are many things to be said, but one thing that we must agree on is that the symmetric group is hidden behind. Let's see what that is. So let's look at the set of configurations of the deck. So I know that you know a little bit of group theory at least. So when we buy a deck of cards, they come in order. I will not talk about hearts and clubs. I'll just say 1, 2, 3, all the way to n. Okay. This will correspond to the identity element. Now, say I was to transpose the top 2 cards, then the configuration will become 2, 1, 3, 4, n, and that is a transposition 1, 2. If you've seen the symmetric group. Otherwise, you can say that we define it this way, that this 1, 2 means that everything else stays fixed. What if we also transpose 4 and 3? So we have transposed 2 and 1, and let's transpose 4 and 3 and keep everything as it is. Then this would correspond to 1, 2, 3, 4. And let me do one more example. Assume from the identity, we bring card 3 to the top, because this is the type of moves we're making now when we shuffle. So we have 3, 1, 2, and everything else in order. This corresponds to the cycle. 1 goes to position 2, 2 goes to position 3, and 3 goes to position 1. Okay, is it clear what we're doing here? So this is the set of configurations is really what is called the symmetric group. And we call it SN, the symmetric. Okay. Now I want, we're still on random to top. I want us to think for a moment of the first time that all cards have been selected. So this capital T is some sort of, it's called the stopping time. It's a time. So it's the first time that all cards have been selected. Okay, now this could take many values. So T could be equal to n plus 1, n plus 2, blah, blah, blah. It might take forever. You know, it's a random variable is what we call it. And we want to study this. Oh, wait, there's something on the chat. Yes, Percy Diaconis is the mathematician. I'm not sure he really likes being called that, but everyone, when people say mathematician, everyone knows it's about Percy. Okay, why can't I close the chat? I'll put it over there. Oh. Okay, yes, and he has multiple books in magic and card shuffling. There is a book that he has with Ron Graham on magical mathematics that is amazing, and I think that everyone would enjoy reading it. It's also quite elementary, so if you want to see something cool, read that book, Magic Tricks and the Math Explained. Okay, so I had just defined this stopping time, the first time that all cards have been selected, and I argue that this is important for random to top. Why is that? So I perform random to top without looking, okay? I don't see what I'm selecting, but perhaps one of you, perhaps Simon, looks at the labels that I pick and he writes them down. And at some point, he says, Evita, right now you have selected all cards. Then I argue that I have no idea, and I have no information about the configuration of the deck at that point. So in other words, we are at a uniformly random permutation. Like every permutation is equally likely to happen. Let's see why that is. So the first time that I bring a card to the top, you must agree that I have no idea which card is on top because it's uniformly random. It could be any of them with equal probability. Okay? Yes, we will get exactly to the expected value of T. That's exactly what we're going to be doing soon. I saw a question on the chat. So, but first I want to explain, and that's what's called coupon collecting, understanding T. That has to do with coupon collecting. But first I want to explain why it is important for the card shuffle I introduced today. So we pick, as I said, the first time I bring a card, it's a uniformly random card. Now, I keep on doing this. Again, I don't look at the labels, and it might be that I pick the same card and keep it on the top. But once I pick a new one, then Simon says, okay, now you have the next new card on top. And I have no idea in what order these two cards are because I'm doing things uniformly at random. It could be that I put the big one on top and the small one right below, or the other way, that I pick them on the reverse order. So both ways are equally likely to occur. Third time a new card is moved to the top, then all 6 possible configurations are equally likely. Okay, how do I turn this off? There we go. So because again, I don't know whether I brought them in order like big, medium, small, or medium, small, big. All these configurations are equally likely. So similarly, the first time that all cards have been selected, which is what this time, this is how we define this time, then all permutations are equally likely to all permutations are equally likely to appear. So let's write this down. We say that this event, if I know that this time has happened, implies that the configuration of the deck is uniform among all permutations of Sn. This is because, as I said, each ordering of the cards is equally likely to occur. Because, as I said, I have no idea what I'm doing. It's just that someone else, Simon, is looking at what I'm doing and he's telling me, okay, this has happened. Okay, so indeed now, to understand how long it takes to shuffle, we will study the expected time of T. So one way to understand things is, and I'll define this in a moment. So I'll give a definition of what is the expected time of T, in case you haven't seen this. So roughly, it means roughly how long does it take for T to happen? That's what this quantity will capture. Okay, so at first, let's make sure we understand what probability is like. So if we were to study, okay, what's the probability that capital T is equal to T, then we would have to count always of selecting cards up to time T, so that all cards have been selected. Let me erase this. I think I need more space. Oops. Have been selected for the first time at time T. So we need to really work hard to count all these ways and then divide them by n to the T, which is, you know, at each step you have n choices of which card to select. Second, again, n, and so on. So this is basically all possible choices we have.
Just to clarify,
Yes.
like when you're pulling the cards up to the top, you can choose the card that's already at the top,
Exactly.
right?
Exactly. So you can repeat things quite a lot. And at first, you know, you might not be doing that, but once you select more and more cards, like for example, what if you have selected half of the cards already, then it's quite likely that you will be picking them again. So that delay, that adds to some delay.
Yeah, but like if the top of the pile is like some card, you can pick that top card again, right?
You can, yes, you can.
Okay.
Yeah.
Okay.
Mm-hmm. Okay, so the reason why I'm writing this is because it's quite annoying to compute this type of thing. So we won't do that. But yes, you'll see. I mean, so I have a question in the chat about the linearity of expectation solution. Exactly, we will get there. Within 5 minutes, you see exactly how it is done if you want. I mean, if you want to work on it on your own, you can also do that. But so what we're gonna do is that we are going to take the time interval. So we're back to understanding the expectation. We're gonna take the time interval 0t, and we're gonna break it into pieces, T1, T2, T3. You'll see in a moment what these things are. So Ti, let me define this carefully, is the first time I distinct cards have been selected. So Tn, for example, is exactly equal to T. Okay, the first time that all n cards have been selected. And then out of convention, T0 is 0. Okay, then T, which again is equal to Tn, can be written as the sum of these differences. So this is a telescopic sum. Let's see. So we get Tn minus 1 plus Tn minus 1 minus Tn minus 2 plus blah, 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 plus T 1 minus T0, and T0 is 0. So you see a bunch of cancellations. You know, this term will cancel out with this term, this one and the next one, and so on. So everything will cancel out, but Tn and T0 will survive, and T0 is 0. Okay, so we're getting to the linearity thing, meaning that now we are going to study these time differences. So set Wi to be, Ti minus Ti minus 1, which is the time that it takes, to pick the ith new card after I minus 1 cards, distinct cards, have been selected. Okay, so it's a waiting time. That's why I use the letter W, I'm sorry. And this is much more easy to study. So if we are to write the probability of Wi is X, well, then let's take a look. So let's write it down. So number of ways to select the new ith card, let's say, the ith new card, after X steps. And then we'll divide it by the number of all such configurations. So let's see what happens. So we take X steps. On the first step, so let's do it slowly. So we have I minus 1 bad cards. Let's write it this way, meaning that if I select from this I minus 1, I'm not contributing a new card. And then I have n minus I plus 1 good cards, or without a plus 1, actually. Oh, no, with a plus 1. No, with a plus 1. Okay, so if we select something from this pile, we're good, meaning that, you know, we added the ith new card. If from here, that's bad. So the event that Wi is equal to X says that for the first X minus 1 steps, we selected a bad card. So how many ways does this happen? Well, we picked one of the I minus 1 out of all choices, which were n, and we did this X minus 1 times. But then at the final step, we selected a good card, which happens with probability n minus I plus 1 over n, meaning we selected one of these good guys, divided by all the number of all cards that we could have selected. Okay, so this was quite easy to write down now. As a probability. And this means that we could attempt at least to compute the expectation. So we will look at the expectation of Wi, which again is, you know, the average value. The definition for the expectation is we add over all x's, so 1 to infinity, the value x, because that's, you know, Wi is equal to x, hopefully, times the probability of wi being equal to x. So, you know, guys that are not very likely to occur will not contribute that much, is the idea. Okay, so we have computed what the probability is. So now we get a geometric sum. So it's funny now that x is the index and I is a parameter, but bear with me. I'm just copying the formula from above. So this, replace this part. Now this guy does not depend on x, and we're summing over x, so we can take it out. And for a moment, let me just write down the answer to this sum, and we will look at it in a moment. Okay, so the answer is to take the probability of success and reverse it. That's what the expected value is. I'll explain in a moment how to compute the sum. I just wanted to say that this is called a geometric random variable. So let me write it here. Whenever you see this type of distribution, that's called a geometric random variable. And the probability of success n minus I plus 1 over n. And whenever you hear, you know, that you have a geometric random variable with probability of success p, then the expected value is 1 over p always. And that's what we got here as well. If you want to compute this type of sum, and I will only give a hint, I want to move on. What you do is that you take the geometric series, perhaps let me change letters. So let's say you have the geometric series, which we know is equal to 1 minus y, and then you can take derivatives as a trick to compute. So differentiate. And if I'm doing this correctly, I think you get this. Yes. Okay, good. So, and then for plug in y to be this thing, and that's how we got that formula, and we also simplified. So if you want to play on your own, that's how you do it. Okay, so all we did now is that we found the expected value for the waiting time. But then we said that capital T is the sum of these waiting times. And indeed, there is linearity, meaning that the expected value for T now, the sum and the expectation can interchange. And we get this, and now I'm gonna plug in the formula. We had n over n minus I plus 1. So let's write down for a moment what this is. Let's write a few terms. So for I equals 1, just a moment, then we start with, oh yes, good. Yes, I was doing something wrong. N over n. I equals 2, n over n minus 1. And then the very last term for I equals n, you just get n over 1. So let's factor n out, which we could have done already because we could take it out from the sum. we get this sum, and I don't know if you recognize it. This is the harmonic series. We can write it this way. And I don't know if you know that this harmonic series works like log n. So indeed, the statement about n log n has to do with n being big. So their theorem is, about bigger. So n's. So for fixed n, you can compute this explicitly. You don't need to say this. You don't need to bring a logarithm. But for bigger n's, you say that the expected value for this capital T is n log n. Any questions? If there are no questions, then I will move to riffle shuffles, which is what I promised you at the beginning. That's all. And again, the idea will be quite similar. We will again have some stopping time that captures the behavior. Now, instead of doing exactly riffle shuffles, we're going to be doing inverse riffle shuffles. And you see in a moment that these two are connected. So again, we start with a deck of n cards. And now for each card, we independently flip a fur coin. Independently means that the outcome for card 1 should not have anything to do with the outcome of card 2. It doesn't influence, and so on. One card doesn't influence the other. Now, if heads, mark the card with 0. You'll see in a moment why I do that. And move it, mark a card with 0. Let's stop there for a moment. If tails, mark it with 1. And now what we do is that we remove the 0 cards from the deck. And we move them to the top. Keeping the relative order fixed. So the 0 cards keep the relative order, the 1 cards keep the relative order, but now all of the 0 cards are above all of the 1 cards. So earlier what we were doing is that we were cutting the deck into 2 and we were riffling. Now we have the deck, we riffle, we unriffle, meaning that we do this. So that's why it is called inverse riffle shuffle. We really do the inverse move. And again, one could have different coins per card. As long as we're independent, we're good. But the mixing behavior will change. So the mixing result I will discuss today is not the one by Bayer and Diaconis that I promoted. It's just that, if you ever read, there is a New York Times article about riffle shuffles, and there you'll see the 3/2 log base 2n. I did not want to give you a different answer immediately. The one I will present today, however, is due to Aldous and Diaconis, which gives a different constant. And in case you wonder, all that changes is the metric that we study the card shuffle with. So there is a metric where 3/2 log n, log base 2n is the correct thing. And there is another pseudo metric, perhaps that's not even the correct term to use, but something that behaves like a metric called separation distance, where a few more steps are required, and it's 2 log base 2n steps. And that's what we're gonna do now. Okay, so is the definition clear? So to define now the stopping time for this card shuffle, we will build an array. So let's see how we're going to do this. And I don't want to mess this up. It's delicate. So the columns will have the labels of the cards. So let's do 1, 2, 3, blah, 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 n. And here we will have, okay, time, time. So meaning first step, second step, third step, fourth step, blah, 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 t step. Okay, so as t grows, this array becomes bigger and bigger in terms of numbers of columns. And all we do is that in the entries, we record whether the card got a 0 or a 1. So perhaps we got 0, 0, 1, blah, 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 0 first time. I don't know. We just write a few. And so on. So at time t, we record whether card I got assigned a 1 or a 0. Okay, that's what we do. That's what we record over there. Okay, so far so good. Because the stopping time I'm going to define has to do with this array. So now what we will care about is the first time that all rows sorry. First time that the array has n distinct rows. Okay, so let's do an example. I will argue that this will capture the mixing behavior. That when this time, so we argue that knowing that this time has happened implies that the deck is at a uniformly random configuration. And therefore we are shuffled. Example. So perhaps we have cards 1, 2, and 3. And let's say at time 1, I just want to copy my example not to mess things up. We get 1, 1, 0. So well, okay, I see a question in the chat. The question says whether here we should have equality or less. So once you are at the uniformly random configuration, if you continue doing this, you remain at a uniformly random configuration. So you're right that we should care about the very first time, you know, the equality, but understanding, but it's okay if you take extra steps. Okay, so this statement is wrong. It's not wrong. And in fact, I want to write it this way because before we studied the expectation, now we will study the probability that T hasn't happened yet. Okay. So I'm just playing here with an example, and I'm saying that perhaps at time 1, the outcomes were 1, 1, 0. At time 2, I have 0, 0, 1, perhaps, and now still I have 2 rows that are equal, the first and the second one. So perhaps on the third step, okay, it doesn't have to be a symmetric, it doesn't have to be a square array, just in my example, it happened. Perhaps we got 1, 0, 0, then now, and after 3 steps, we have separated, meaning that this capital T has happened. We have 3 different rows. Okay, now I want to try to explain why knowing that T has happened is enough for us to know that we're mixed. So the way to do this is to reverse the rows. So first row, I'm not saying it correctly. We're not reversing the rows, we're reversing each row. So the first one will remain as is. The second one, it will be 0, 0, 1. And the third one also remains as is. Okay? And now we look at those things as vectors in binary. So let's remember that this is for card 1, this is for card 2, this is for card 3. And we will sort them from smaller to bigger. So let me do this correctly. So this is the smallest. Then this is the next one. And then this guy is the biggest. And so this says that the deck should be in the following configuration. So card 1 corresponds to this vector. Card 3 corresponds to this vector, and card 2 corresponds to this vector. So what I'm trying to say is that once I have distinct rows, I can tell you, if you give me the rows, then I can tell you the exact configuration of the deck. Because the zeros and ones keep track of whether I moved up or down. And by sorting the reversed rows, and then saying, okay, this row corresponded to card 3, this row corresponded to card 2, bringing back the cards, then I can tell you what the order of the deck is. So, however, T does not ask what are these rows. T only asks for the first time that we have distinct rows. That's all it asks. And so again, every order of these rows is equally likely. So let's write it down. And for now, perhaps I'll say equality, but it doesn't matter. As I said, we remain uniform. When T happens, we know that we have n distinct rows, and therefore we can do the sorting, because if you had 2 cards with equal rows, then you cannot distinguish between them. But we don't know which vector, for example, corresponds to which card. In particular, any ordering of the rows is equally likely to occur. And this is because our coins were fair, for example. So here we have this card to be, this vector to appear at the very last card, but it's equally likely if we transpose these 2 rows, that configuration is also equally likely. That's all I'm trying to say. Okay, so the fact that we don't know the order tells us that we are at a uniformly random permutation when T has happened. So this is how to explain this. And again, I am not looking at the array, but someone else is keeping track of what I'm doing, and they can tell me, oh, Evita, right now the array has distinct rows. So now for the rest of our discussion, I want to discuss this capital T. It's a different capital T than before. And it's connected to what is called the birthday problem. So well, before I told you it was coupon collecting. I'm not sure I wrote it down, but these are two famous problems in probability. And, instead of just talking to them about you, I thought it would be cool to learn about them through card shuffling. So the birthday problem says, what if we have how many people? Let's say there are M people. And we ask, what is the probability? Again, let me state it correctly. That there is no pair of people sharing the same birthday. Okay, so if we want to write this probability of, let's call this event A. I don't want to have to copy it again. So if we look at the probability of A happening, then again, we start counting. So in the numerator, we'll have, wait, there is a question. I think someone is raising a hand. Perhaps it's an accident.
No, I have a big-
Yes. No. In math, I agree with you. In math, we agree in the convention that we have 365 days. That's one question. Is that what you wanted to ask as well? Most likely. So we make the convention of 365 for now. Okay, so you're right, but that's the convention. So for the first person that we select, we have 365 options. Let's say Julius Caesar hasn't happened yet, so we have not corrected the calendar because before Julius Caesar there was no October 29th. Okay, so we have 365 choices for person one, then 364 for the second person, because we cannot give the second person the birthday that the first person had. 363, blah, blah, blah. And then we stop at 365 minus M plus 1. Okay, that's the number of ways of having different birthdays pairwise. And the bottom is, we can have any choices, no restrictions. So 365 choices for all of them to the end. Okay, so that's the birthday problem. Let's try to put this down now and use it for the inverse riffle shuffles. So we want to look at the event that at time t let me write it correctly. Okay, perhaps at time k, just for consistency with my notes. At time k, the array, let's say, has distinct pairwise, so pairwise distinct rows. I'm trying to be careful with the English to be clear. Okay, so now at time k, we have 2 to the k possible vectors. Okay, so 2 to the k, 2 to the k minus 1. We do exactly the same thing as before. Blah, blah, blah. We have n rows. So I'm doing exactly what we did for the birthday problem, but now the numbers change. While we have 2 to the, oh, wait, just a moment. While in total we have 2 to the k for all of them, so times n. Okay, I think I did this right. The analysis there is always, too many symbols and so on. So if we are to look at the probability that the capital time t has not happened So here we have at least two rows that are still the same. We're gonna take this and say that, look, this is equal to 1 minus the probability that T has happened. Okay, so there are two possibilities, either T has happened or T has not happened. And so in English, the fact that K has happened, it means that a time K, the array has pairwise distinct rows, which is exactly what we computed. Okay, so we're gonna bring this now. I'm gonna write it in a more succinct formula. So I just abbreviated this product. I put this product in this form. That's all I did. Okay, and then I do want to show you a little bit of this analysis just to get a feeling of how we get the statements. So the main thing really that appears all over card shuffling is the fact that if you take 1 minus 1 over m to the m, this behaves like 1 over e as m goes to infinity. So again, the statements are for n going to infinity, so big cards. So going back to the probability that capital T hasn't happened, and now we have this. Let's put it together. So we are going to put this inside the product. So the n will disappear because this will go to every single term. Let me do it carefully. Okay, then we are going to turn this, and now it's a heuristic, but it can be done rigorously. There are inequalities to help us write it very, very carefully. I just don't want to get too technical here. We are gonna replace this as e to some power, so using this fact. So 1 minus, let me do it correctly. N or n minus 1, I'm not sure here I have the correct thing, but it doesn't matter much. So e to the minus, so we get e to the something. We need to make sure that here we need to have, we needed to have, let me write it with a different color. For us to say that this behaves like e, we should have had 2 to the k over I minus 1. You know, this minus 1 really bothers me. I want to turn this instead. I think if I were to write this, I should be okay. Here, probably it was from 0 before. So I just don't want the I minus 1. It bothers me. So let's go back. To use that fact, we would need here on the exponent to have this guy reversed, but we don't have that. So to make sure that we have the correct thing, we also need to multiply by this so that we cancel. So now this thing, behaves like 1 over e, is what I'm trying to say. And so the rest remains. Okay, this is how we do the analysis. And the product can go as a sum in here. And now this is a sum that we know how to compute. So the 2 to the k comes out. And we have the formula. I don't know if you guys have seen this. I'm pretty sure you have. So that if you add 1 plus 2 plus 3 plus blah, 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 all the way to n minus 1, I guess. Then this is n minus 1 times n over 2. Okay, so we bring this back. Okay, and so now we need to make this small. So we are going to take k to be log base 2 in order to kill this 2 of n squared to kill the top. And if we take, say, a few more steps, then the probability that t hasn't happened is something like 1 minus, we have killed this term. I don't like the 1 minus for a moment. Oh, yes, good. Or something like that. C plus 1 possibly, roughly, I'm not keeping track of the plus ones. So this is what we have proven. And let us see what it does. So if we send c to infinity, then this denominator becomes infinity, which means that this becomes 0, e to the 0 becomes 1, so this is tiny, 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 tiny. Okay, so the statement makes sense, meaning that we wanted something small. So k here, I should change this. The k that we have used is exactly log 2 log base 2n plus c. Let me write it up more nicely. We say that if we take more than these many steps, then this is something that goes to 0. It's something small. Okay. So I mean, I know this might be a little bit too much. And for the last few words I wanted to say is that the techniques, this capital T thing that I discussed today, the stopping times, these are called actually strong stationary times. Which is, as a definition, is, if they have happened, then this implies that we are shuffled. So if you ever hear the term strong stationary time, that's where it comes from. It is one major technique in card shuffling. If you have a nice shuffle and you can study the behavior by finding a stopping time that guarantees that you're mixed, that's not too common, but not too rare either. But there are other techniques to study card shuffling. And so, for example, there is this very famous card shuffle about random transpositions where you pick 2 cards uniformly at random and you transpose them. And there we use algebra to analyze this. So we use representation theory of the symmetric group. If you've ever heard of this, I just want to advertise this. So there we use eigenvalues and eigenvectors of a specific matrix to study these type of things. So all I'm trying to say is that there are techniques from probability, techniques from algebra, techniques from analysis. I just wanted to show you this one because I thought that hopefully it would be understandable. And I think I'll stop there. If there are any questions.
Yeah, thanks for a very interesting talk. So are there any questions for Evita?
So I was like looking through, like I'm doing like an expository paper right now on Markov chains. And while I was reading through one of the texts, like a lot of the techniques that you showed here were very similar to what I had seen in that textbook also used. So I was just wondering, like, are there like Markov chains that are studied with card shuffling or something related to cards in general? Like somehow, like you may want to study like the distribution of like poker games or like with certain hands. I'm not exactly sure if something like that is done.
Oh, you got Siri to search for poker. That's all I have to say.
Yeah.
But there are such things. There are such things. Um, I don't do this type of thing. I do more of the mixing type of thing. And in Markov chains in general, you can ask things like hitting time. So for example, there might be your favorite configuration and you're like, oh, I really need to stop the game if I reach the identity, or I don't know what. And people would study that as well. So there are different statistics that people care about. It's just that, you know, when we talk about mixing times, it's you know, this type of question of how many times do we need to repeat this. For other Markov chains, you know, we don't understand the stationary distribution well. Here in the examples I gave, the stationary measure was uniform. If people don't understand what I'm saying, all it means is that, you know, as we keep on doing the card shuffle that we like, then at the end, each permutation will be equally likely in these models. But if we were to put different weights on the cards for random to top, for example, that would no longer be the case. We will not have the uniform distribution. And for the Zetland library, there's no nice description of the stationary distribution. So there are many models coming from physics, like the asymmetric exclusion process, where people really, really try to understand what the stationary measure is. Many, many different questions one can ask on Markov chains.
Thank you.
Of course. Any other questions?
Okay, perhaps there are no more questions at the moment, so thank you. And so that finishes this part of the class.